Hello viewers, welcome to Adesha Tech Tutorial. So in this video we will be discussing Semiconductor part 2 gate question. So let's begin with the first question. So in this question here you can see drift current in the semiconductor depends upon which of these options. So the first option is only electric field. We know how the drift current is related to the electric field and other quantities. So we can write J, that is the drift current density is represented as J drift, which will be equal to Q times N times mu n. What is N here? N is the concentration of electrons and mu n is the mobility of electrons, plus P times mu P, concentration of holes and mobility of holes, whole into E. So here you can see the electric field is directly proportional to J drift, that is the drift current, and all other quantities such as the concentration, the mobility is also depending on the drift current. So here the drift current in the semiconductor depends upon only electric field? No, it also depends upon other quantities. Let's see other options. Only the concentration gradient. What do you mean by concentration gradient? The concentration gradient is represented by dN by dx as well as dP by dx. So this is for electrons and this is for holes. So these are the quantities related to the diffusion current. Okay. So it is not necessary in this question. So answer B is not our answer. So now here in this bit C you can see it depends upon both electric field and the carrier concentration. Yes, it is depending upon the carrier concentration, that is N and P as well as E. So this can be our answer. And in the option D you can see both electric field and carrier concentration gradient. Again it is related with the diffusion current. So answer D is not our answer. The most appropriate answer here it is C, not A. Okay. So now let's move on to the next question. So in this question you can see a DC voltage, that is 10 volts, is applied across an N-type silicon. Okay. So here the silicon is N-type, having a rectangular cross section of length whose length is 1 cm as shown in the figure. So this is the 10 volts applied and the length of the semiconductor is 1 cm and the semiconductor which we are using is the N-type. Now what happens is the donor doping concentration at this Nd is given, which will be equal to 10 to the power 16 per centimeter cube, and the mobility is also given of electrons mu n, which will be equal to 1000 centimeter square per volt second. So here your Nd, your V first, the voltage applied is 10 volts. Then the length is given, which is equal to 1 cm. Next Nd is given, so here Nd is nothing but concentration of electrons. So it will be equal to Nd, whose value is 10 to the power 16 per centimeter cube. Next what is given? Mu n, that is mobility. So mu n is equal to 1000 centimeter square per volt second. So now what we need to find? We need to find the average time, the time required by the electrons to move from one end of the bar to the other end. So this is the bar given. So this is one of the end and this is the other end. So we need to find out what is the time. So here T will be equal to how much when the electrons will move from position 1 to position 2. So let's find out. So for that what we need? Mu n is given and we need velocity, okay, in order to find time. So now how to find the drift velocity? So the velocity associated here is the drift velocity. So drift velocity is associated with the electric field. So we can find here drift velocity with the help of your mobility and the electric field. Now how to find electric field? So E is represented as V divided by L. So we are having the values of V and L. We can substitute here, and what we will get, it will be equal to 10 volts divided by 1 cm. So what you will get, it is 10 volts per cm. So we got the electric field. So now we can find the drift velocity. Let us represent it by Vd. So Vd is equal to mu n into E. So we know what is E and what is mu n. It is given. So it is 1000 centimeter square per volt second into 10 volts per centimeter. So now we can find out it is equal to, so here centimeter square and centimeter gets cancelled, volts gets cancelled. So what we will get, 10 to the power 4 centimeters per second. Okay, these units you have to find very carefully, otherwise you will get a wrong unit. So now your Vd, you got the Vd. So we will now use a simple mathematical formula related with distance, velocity and time. So here your velocity, how it is depending upon time? Velocity is equal to distance by time. So here Vd will be equal to distance covered, that is 1 cm divided by time, which we require in our answer. So now from here we can calculate the time. So what is time here? Time is equal to distance by velocity. So distance here we can substitute 1 centimeter. So distance is 1 centimeter divided by velocity is how much? 10 to the power 4 centimeter per second. So here 10 to the power 4 centimeter per second. So centimeters gets cancelled. What you will get? 10 to the power minus of 4 seconds. But in which unit we need? We need in microseconds. So how to find out? So here we can write 10 to the power, microseconds is how much? 10 to the power minus of 6. But we are having 10 to the power minus of 4. So we have to multiply 10 to the power minus of 2 in order to get 10 to the power minus of 6. So as we have multiplied 10 to the power minus 2, we have to again multiply it with 10 to the power 2. So what we will get? So here your t will be equal to how much? 10 to the power 2, that is 100 times of, and this is nothing but, here we are having in seconds. So this is 10 to the power minus of 6 seconds, that is nothing but microseconds. So the value of average time here, it is 100 microseconds. Okay, so this is our answer. So next move on to the third question. So in this question here you can see the silicon sample with unit cross-sectional area is under thermal equilibrium. That means it is at room temperature, that is at 300 Kelvin, and the charge is given, which is 1.6 into 10 to the power minus of 19 coulombs, and the thermal voltage is given, which is 26 millivolt, and what is given? Electron mobility, that is 1350 centimeter square per volt second. So here you can see in this figure that the semiconductor used is which type? That is N type. Why? Because here we are having the donor concentration. So Nd is given, that means the semiconductor used is N type. And the distance is also given. The length of the semiconductor is given, whose initial position is 0 and it is ranging to 1 micrometer. So the length here, it is how much? 1 micrometer. Okay, so these are the values given. So now let's find out the first bit of your question, that is the magnitude of electric field at x is equal to 0.5 micrometer. So we need to find here electric field. So now here you can see the electric field is uniform all over the semiconductor material. So it doesn't depend on the distance which is given in the question. So electric field is uniform and we can directly calculate it with the help of the formula V divided by L, because V is given as well as the length is given. So what is V? Here it is 1 volt divided by the length. What is length here? It is 1 micrometer. Don't take 0.5 micrometer. We have to take the total length of the semiconductor, that is nothing but 1 micrometer. So here you can see we can simplify it, and what we will get 10 to the power. So if we need to find it in centimeters, because we are having mobility in centimeters, so we have to convert micrometer to centimeter. What we will get here? We will get 1 volts divided by 10 to the power minus of 4 centimeter. Okay, so 1 micrometer is nothing but 10 to the power minus of 4 centimeter, which will be equal to 10 to the power 4 volts per cm. So this is our electric field. So 10 to the power 4 volts per cm is 10 times of kilovolt per centimeter. Okay, 10 kilovolts per centimeter. So our answer is the C bit, that is 10 kilovolts per centimeter. Now next, moving on to the second bit. So in the second bit you can see what it is given is the magnitude of the electron drift current density at x is equal to 0.5 micrometer is how much? So what is your drift current density? It is J. So here we are going to write it is Jn drift. Why? Because we are dealing with the n-type semiconductor. So Jn drift is equal to how much? Q times of mu n electric into electric field. So we are having the value of electric field from the previous question, and we have n, which is nothing but it is equal to nd, which is equal to 10 to the power 16 per centimeter cube, and we are having the value of the charge. So we can find the Jn drift. So here also we will not consider the distance x is equal to 0.5 micrometer, because we are dealing with the electric field which is constant or which is uniform all over the semiconductor material. So let's substitute the values. It is 1.6 into 10 to the power minus of 19 coulombs. What is mobility? It is 1350 centimeter square per volt second multiplied by the concentration of electrons, that is 10 to the power 16 per centimeter cube cross 10 to the power 16 1 divided by centimeter cubes. Here we have to calculate the units properly. Okay, cross, what is E here? E is the electric field which we calculated as 10 kilovolts per cm. So we will write in volt terms, that is 10 to the power 4 volts per cm. So 10 to the power 4 volts per cm. So now let's see. So here centimeter square and centimeter cube gets cancelled, so remains only 1 centimeter, and here also volts here and this volts gets cancelled. So what you will get here, that is 1.6, that is 1.6 into 1350. So if we multiply this, what we will get here? We will get 216. Okay, 2160 amperes. So coulombs per second is amperes divided by what is left here? Centimeter. Okay, centimeter times centimeter, that is centimeter square. So if we simplify this, we will be getting 21600 amperes per centimeter square. Okay, so this is our answer, which is nothing but it will, you can also write it as 2.16 times of 10 to the power 4 amperes per centimeter square. So our answer is A bit, that is 2.16 into 10 to the power 4. So here it is little mistake here. It is everything is in power. Okay. So here it is in square and powers. Okay. So our answer is 2.16 times 10 to the power 4 amperes per centimeter square. So let's move on to the next question. In this question you can see the dependence of drift velocity of electrons on electric field in a semiconductor. Okay. So here the drift velocity is given. So here the drift velocity is given with respect to the electric field. So there is a graph between drift velocity Vd and the electric field. So there is dependence between the drift velocity and the electric field in a semiconductor. So the semiconductor has a uniform electron concentration of this much. So it is having an electron concentration, that is N, which is nothing but 10 to the power 16 per centimeter cube, and electron charge. So Q is given here, which is equal to 1.6 into 10 to the power minus of 19 coulombs. So if a bias of 5 volt is applied across A, so if 5 volts voltage supply is given across the semiconductor whose length is 1 micrometer, the resulting current density in the region, so here we have to find the current density, which is nothing but J drift. Okay, so drift current density in this region in kiloamperes per centimeter square is how much? So as we are dealing with the N-type semiconductor, so here your J and drift is nothing but it will be equal to how much? Q times N times mu1 into E. So here first we have to get the value of E. How we can get? We are having the supplied voltage and the length. So supplied voltage is 5 volts and length is 1 micrometer. So we can easily find electric field here. So E is equal to V divided by L. So what is V here? V is 5 volts. Okay, so this is 5 volts. And what is L here? 1 micrometer divided by 1 micrometer. So we are dealing with centimeter, so we have to convert it into centimeter. So here 5, so by converting it to centimeter, what we will get? 10 to the power minus of 4 centimeter. So we can directly write, we will take it to the numerator and we will get 10 to the power 4, okay, volts per centimeter. So this is our electric field. Now there is, in this graph you can see there is a relation between the drift velocity and the electric field. So with this we can find the drift velocity. So we got the electric field here. Okay. So now before calculating that we need to find the drift velocity, and then we are going to calculate the Jn drift or the drift current density. So how to get the drift velocity when electric field is 5 into 10 to the power 4 volts per centimeter. So here, so this is 5 into 10 to the power 5. So 5 into 10 to the power 4 is somewhere here. So it is, its value is 5 into 10 to the power 4. So at this position you can see we will also have as the slope in this linear region. So the drift velocity here, it is somewhere here. Let it be x. So we need to find out x in comparison with the given drift velocity and electric field. So your x is going to lie, the slope is going to lie on this linear region. For the electric field, 5 into 10 to the power 5 as well as 5 into 10 to the power 4. So we can use, we can write the slope of the graph mathematically as, we can write here the given drift velocity, that is 10 to the power 7 divided by the given electric field 5 into 10 to the power 5, which will be equal to the required drift velocity, which is x, divided by 5 into 10 to the power 4. Okay, because the question is asked to find the drift velocity. Okay, so we cannot directly put the formula here because the question is asked with respect to drift velocity, which is here it is equal to x. So we cannot directly put the formula this one and find the and substitute the electric field. So we have to find here a drift velocity in order to find J and drift. That is, we have to put the formula here Q and V d, okay, or it is V drift. So here the Vd is nothing but it is equal to x. So here your Vd is equal to x. So let's first find out what is our x. So here we can cancel these two. We can simplify it, and what we will get? Okay, so x is equal to 10 to the power 6. Okay, so x value is equal to 10 to the power 6, which is nothing but the required drift velocity, and its unit will be centimeters per second. So here we got x, which is equal to, let's represent it as Vd dash. So it is equal to Vd dash, and we can substitute and find our J and drift. Okay, so just don't make mistake, because considering this graph we need to find our answer. So first we will get the electric field and the velocity associated with the drift velocity associated with the electric field we got to find, and then we need to find the J and drift. So J and drift is equal to Q times, that is Q is 1.6 into 10 to the power minus of 19 into N. What is N here? 10 to the power 16. So this is in coulombs. 10 to the power 16 per centimeter cube, that is 1 by cm cube. Okay, into the drift velocity, which is 10 to the power 6 centimeters per second. So here your centimeter gets cancelled, and here we are having centimeter square. So here you can see what we will get. So here 10 to the power 16, you will get 10 to the power minus of 3 or 10 to the power 3 here. So the value here, it will be equal to 1.6 into 10 to the power 3. Okay, amperes per centimeter square. Okay, coulomb per second is your amperes. So here it is nothing but it is equal to 1.6 into 1.6, 10 to the power 3 times of ampere is kilo amperes per centimeter. It is a straightforward question. We are getting directly in kilo amperes per second square. So here our answer is 1.6 kilo amperes per centimeter square. So this is all about this question, and we got our answer. So you have to see carefully the graph. So first find out what is the electric field, then with respect to this electric field, by considering the linear slope of the graph, we need to equate the slopes and find the drift velocity, and then substitute the drift velocity in order to find the drift current density. Okay, so here in this question you can see an n-type silicon bar is given whose length is 0.1 centimeter. So here length is 0.1 centimeter and cross-sectional area, whose cross-sectional area is 100 micrometer. So here cross-sectional area A is 100 micrometer square, and which is having a majority carrier concentration, that is N here. Okay, the concentration of electrons, because the semiconductor is n-type, which is 5 into 10 to the power 20 per meter cube, and the carrier mobility. Okay, so here it is electron carrier mobility because the semiconductor is n-type. So mu of N is 0.13 meter square per volt second at room temperature, that is 300 Kelvin. So now if a charge of electron, which is 1.6 into 10 to the power minus of 19 coulomb, that is Q, is given, then the resistance of the bar is how much? So we need to find out the resistance. So resistance in terms of resistivity can be written as R is equal to rho L divided by A. What is rho here? Rho is the resistivity. So in terms of conductivity, it is the inverse of conductivity. So it can be written as L divided by sigma. Okay, sigma is the conductivity, sigma of n for n type, into area. Okay, where rho is equal to 1 by sigma. So we can write the formula for sigma n. So here L divided by sigma of n is q n mu n into A. So now we can substitute the given values and find what is R. So R is equal to, L is how much? 0.1 centimeter. We need to convert it into meters for easy calculations because your concentration and mobility is given in meters. So here it is 0.1 into 10 to the power minus of 2 meters. Okay. So now we will be substituting for Q. Q is 1.6 into 10 to the power minus of 19 coulombs times n. N is 5 into 10 to the power 20. So 5 into 10 to the power 20 per meter cube times mu n. Mu n is mobility, which is 0.13. 0.13 meter square per volt second times our area. Area is 100 micrometer square, which is 100 into 10 to the power minus of 6 square meter square. So here 100 into 10 to the power minus of 6 square is 10 to the power minus of 12 meter square. So now here our R becomes 0.1 into 10 to the power minus of 2. So first simplify for the unit. So here meter square, meter cube gets cancelled. Here one of the meter with meter square gets cancelled, and here meter gets cancelled. So we are not getting any unit in the numerator. So here what is left behind? Now just cancel the power terms. So 10 to the power minus of 19 gets cancelled with 10 to the power 20, and here we can take it to the numerator. So this is what? 10 to the power minus of 10. So here it becomes 10 to the power 10. And here we are getting 1.6 into 5 into 10 into 0.13, that is 1.3. Coulombs per second is ampere, so we are getting ampere per volt in the denominator. So this is 8. So decimal point gets cancelled here. So this is 1 into 10 to the power 8. 1.6 into 5 is 8 into 13. So here the value which we will get is, in the denominator, is 104. So here we can take it out, 10 to the power 3, 10 to the power 2. So here 100 into, how much is left? 10 to the power 6 volts per ampere. Okay, after taking this unit to the numerator, we get volts per ampere, which is nothing but ohms. So this value is approximately equal to 1. So this value is 1 into 10 to the power 6 volts per ampere is ohms. So 10 to the power 6 is our answer. So our answer 6 is option A, that is 10 to the power 6 ohms. Question, it is given that a silicon sample is uniformly doped with a donor type impurity. So donor type means the semiconductor is N type with a concentration of 10 to the power 16 per centimeter cube. The concentration is also given, that is the electron concentration, that is 10 to the power 16 per centimeter cube. The electron and hole mobility in the sample. Electron mobility is given, hole mobility is also given. So electron mobility is 1200 centimeter square per volt second, and hole mobility is 400 centimeter square per volt second. Assume complete ionization of impurity. So we have already discussed in other questions complete ionization. That is, if there is complete ionization, your donor impurities will be equal to your electron concentration. So here your ND will be equal to N in case of complete ionization. The charge of the electron is given and the resistivity of the sample in ohm cm is how much? So we got to find the resistivity. So it is quite simple. So now in this question you can see it is a n-type semiconductor. So as it is a n-type semiconductor, we will also only consider the electron mobility, that is 1200. Will not consider the hole mobility because the concentration of holes is very less. So we are not going to consider the hole mobility. So 400 we will not be using here. And we need to find the resistivity of the n-type silicon now. So resistivity is nothing but rho, which is equal to 1 by sigma. So what do you mean by sigma here? It is 1 divided by q times n times mu n. So all values are given. So we can substitute. So 1 by, what is q? 1.6 into 10 to the power minus of 19 coulombs cross n. What is n here? It is the donor concentration or electron concentration, that is 10 to the power 16 per centimeter cube. So here 10 to the power 16 per centimeter cube, and last is your electron mobility, which is 1200 centimeter square per volt second. So here your cube and complete square gets cancelled. What you will be getting? It is 1 into, so here you will get 10 to the power minus of 3. 10 to the power minus of 3 and here 10 to the power 2. So you will be getting 10 to the power minus of 1. So we can take it to the denominator and here you will get 1.6 into 12, okay, amperes per volt cm. So amperes per volt cm is nothing but, if we simplify it, we will be getting the value as 0.52, okay, 0.52 ohm cm. Here when we will take it to the numerator, what you will be getting here? Volt per ampere cm. So volt per ampere is nothing but it is ohms. So our answer is 0.52 ohm cm. So this is our answer in ohm cm. So the answer is 0.52 ohm cm. So this is quite straightforward and simple question. Just you have to avoid here the hole mobility. You will get your answer correctly. So here in this question you can see a graph is plotted between ln of rho I. What is rho I here? Rho I is the intrinsic resistivity and we are considering an intrinsic semiconductor. So the graph is between ln of rho I and the inverse of temperature, that is 1 by T. And this graph is almost a linear plot. So from this what we need to find out, the plot of the given line can be used to estimate, given linear line is used to estimate which of these options. So let's find out what is rho I first. So here your rho I will be equal to 1 by sigma of I. So as we are considering an intrinsic semiconductor, so here your N will be equal to, so here N is equal to P is equal to N I, that is the intrinsic concentration. So we can take intrinsic concentration as common in the equation of your conductivity sigma of I. So this is 1 by Q times, we will take the concentration common, that is Ni. What will be left behind? Mu n plus mu p. So this is our intrinsic resistivity. So now what is Ni here? So Ni can be written as, A, that is the cross-sectional area of the semiconductor, times the temperature to the power 3 by 2 times exponential to the power Eg divided by 2 kT. So this is our formula for the intrinsic concentration. This you got to remember. This can also be proved, but at this time being, we don't require the proof. So here we can substitute Ni here and find an equation for rho I. So rho I is equal to 1 by Q times A. Okay, when we'll substitute Ni, we can take to the numerator to the denominator the temperature. So we are taking the area at the same position, and we have to take the temperature to the numerator. So T to the power minus of 3 by 2 and exponential is minus of Eg times, this is minus of Eg, okay, in the formula. So here it will become plus of Eg times divided by 2 kT. And what will happen to mu n plus mu p? So it is again a constant value. So mu n plus mu p inverse. Okay, so this is also a constant. So 1 by qa is the constant value and mu n plus mu p is also a constant value. So now we can take ln of sigma rho of I is equal to, so we will take constant as 1 by qa. So here at the numerator we are having mu n plus mu p whole inverse. Okay, so this is a constant value. And what is the ln of t to the power minus of 3 by 2? It is minus of 3 by 2 the ln of t plus Eg divided by 2 kT. So here Eg divided by 2 kT times 1 by 2 and ln of E is 1. So this is the equation for ln of rho I. So here this value is constant. So your plot will not determine the constant value. So what the plot will determine? It will determine the ln of temperature T and the quantity Eg, and all other are constant values. So here Eg is very important. So our graph will determine the band gap energy, which is the option A. Okay, band gap energy will be determined by the linear graph which is between ln of rho I and 1 by T. Let's see the other options also. So here it is given the electron and hole mobility summation. So the graph will not determine because this is a constant value. And in the C option also you can see it is inverse of mu n plus mu p. This is also a constant value. So it is not going to determine that. And last option is the intrinsic carrier concentration. No, it will not determine the intrinsic carrier concentration. It will determine the band gap energy, that is Eg. So you got to remember the intrinsic concentration formula in order to solve this question. Okay, so don't confuse with mu n plus mu p, as it is directly visible in this formula, because mu n plus mu p is a constant, it is not a variable. So mu n plus mu p will not be our answer. Our answer will be the band gap energy. So in this question you can see the resistivity of a uniformly doped, okay, the resistivity is given of a uniformly doped n-type semiconductor is 0.5 ohm cm. So rho is given for an n-type, so it is rho n, which is equal to 0.5 ohm cm. If the electron mobility mu n is given as 1250 centimeter square per volt second. So mu n is also given, which is equal to 1250 centimeter square per volt second. And the charge of an electron is given, which is 1.6 into 10 to the power minus of 19. We got to find out the donor impurity concentration, that is Nd, in the sample. So here Q is given and we got to find out the donor impurity concentration Nd, that means we have to find out what is N. That is the electron concentration, which is nothing but donor impurity concentration, ND, and its unit will be per centimeter cube. Okay, so now just write down the formula for rho n, which is equal to 1 by sigma of n. What is sigma here? Sigma is the conductivity. So this is equal to 1 by q times mu n. Okay, so this is the formula for sigma n. So we can substitute rho n now. Rho n is so here we got to find out n, which is equal to nd. So we can substitute in place of n, nd. So we can simplify the equation, find out nd, which is equal to 1 by rho n q times mu of n. So here just substitute the given values. So our nd will be equal to rho n, which is equal to 0.5 ohm cm cross q, that is 1.6 into 10 to the power minus of 19 coulombs times our mu n. Mu n is 1250 centimeter square by volt second. So here you can see your centimeter into centimeter square becomes centimeter cube, and ohms is cancelled by coulombs per volt second. Okay, coulombs per volt second is nothing but it is inverse of ohms. So ohms gets cancelled, and our value, if we simplify it, we will find our value as 10 to the power 16 per centimeter cube. Okay, so this is our answer, which is nothing but option B. Now next move on to the, so here in this question you can see it is given that a heavily doped n-type semiconductor has the following data. Electron to hole mobility ratio is 0.4. So here the mobility ratio is given, that is hole to electron. Okay, mu p by mu n ratio is how much? 0.4. And what is given? The doping concentration. So here the doping concentration is 4.2 into 10 to the power 8 atoms per meter cube, which is nothing but N. As the semiconductor is N type, so this is nothing but electron concentration. Next, what is given? The intrinsic concentration, which is equal to 1.5 into 10 to the power 4, which is nothing but Ni. What we need to find? We need to find the ratio of conductance of N type, that is represented by sigma of N, conductance of N type, divided by the intrinsic conductance. Okay, the ratio of conductance of N type and that of intrinsic semiconductor. So sigma of I. We got to find out the ratio of conductance of N type and the intrinsic semiconductor of the same material at the same temperature. So here we can directly substitute the formula, that is Qn mu n divided by sigma of I. So in sigma of I, your n is equal to P is equal to Ni. So we can take Ni common. So Q Ni, and in the brackets what we will get? Mu n plus mu p. So here we got to consider both the mobility of electrons and holes. So in the denominator we can take mu n common in order to get the ratio mu p by mu n. So here Q Ni mu n common. So in the brackets what we will get? 1 plus mu p by mu n. Okay, so here Q gets cancelled, mu n gets cancelled. So we can substitute all other values which is given. N is given and Ni is also given, and what is given? Mu p by mu n. So we can substitute that. Substituting the values of N, what we will get? 4.2 into 10 to the power 8 atoms per meter cube divided by 1.5 into 10 to the power 4 atoms per meter cube into 1 plus mu p by mu n, which is nothing but 0.4. So here we are going to get, so here meter cube gets cancelled, we will get a ratio 10 to the power 4. So here remains 10 to the power 4. So after simplification, you will be getting the ratio as 2 into 10 to the power 4, that is nothing but 20,000. Okay, so answer D is our, option D is our answer. Okay, now next moving on to the 10th question. So here in this 10th question you can see a silicon sample A is doped with, so here A is doped with 10 to the power 18 atoms per centimeter cube of boron. So when it is doped with boron, that is having at valence electron 3, so it is a p-type semiconductor. Now another sample, so A is a p-type semiconductor. Another sample B of identical dimension is doped with 10 to the power 18 same atoms per centimeter cube of phosphorus. So here phosphorus is having 5 valence electrons, here boron is having 3. So here 5 means your B is a n-type semiconductor. So ratio of electron to hole mobility is 3. Okay, so electron to hole mobility, that is mu n by mu p. Okay, electron to hole, so this you got to read it clearly, whether it is hole to electron or electron to hole. It is electron to hole, whose value is equal to 3. So the ratio of conductivity of the sample A to B. So we got to find out A to B, that is sigma of P, conductivity of the A type, divided by sigma of N, that is the for n type, which is for the sample B. So here we can put the formula. So sigma P is Q times P times mu P divided by Q times N times mu N. So here the value of your P, that is 10 to the power 18, as well as value of B, that is N, is 10 to the power 18. So P and N are same, so we can cancel P and N. Q is also getting cancelled. So mu P by mu N. What is mu P by mu N? It is, the mu N by mu P is given as 3. So this implies your mu P by mu N will be how much? Inverse of 3, that is 1 by 3. So we will substitute here 1 by 3. So our answer is option B, which is equal to 1 by 3. So here in this question you can see the electron concentration in a sample. So electron concentration is given of an n-type silicon at room temperature, which is varying from 10 to the power 17 per centimeter cube to 6 into 10 to the power 16 per centimeter cube. So 10 to the power 17 per centimeter cube is at the initial position of the semiconductor, that is x equal to 0, and 6 into 10 to the power 16 is at some position where x is equal to, at the distance covered by the electrons, is 2 micrometer. So here we can find the concentration gradient or the slope of the semiconductor. So here it is dN by dx is represented as slope, final minus initial. So how we will find the slope? Final minus initial ratio. So here the final value is, final concentration value is 6 into 10 to the power 16 per centimeter cube minus 10 to the power 17 per centimeter cube, which can be written as 10 into 10 to the power 16 per centimeter cube, so that the calculation become easy. So we have to write in this manner, divided by how much? The final distance, that is 2 micrometers. So we are here, we will be having in centimeter. So 2 into 10 to the power minus of 2 centimeter minus of 0 cm. Okay, so here what value we will get? we will get minus 4 into 10 to the power 16 divided by 2 into 10 to the power minus of 2 per centimeter to the power 4. So here the final value is how much? Minus of 2 into 10 to the power 18 per centimeter to the power 4. So we got our concentration gradient. So this is a question consisting of concentration gradient of electrons, which is nothing but we got to find out the diffusion current density. Okay, so what are the other values given? Assume a situation that electrons are supplied to keep this concentration gradient constant with time. Okay, the concentration gradient is kept constant with time as the value, the graph is linear, so this concentration gradient is remaining constant over time. If the electron's charge is 1.6 into 10 to the power minus of 19 coulomb and the diffusion constant dn is given as 35 centimeter square per second, what is the current density in the silicon? Okay, so we need to find the diffusion current density if no electric field is present. So we all know that to find the diffusion current density, we need not find any kind of electric field or no electric field is given, then only we can find the diffusion current. So here your diffusion current is represented by, it is due to the electrons because the semiconductor used is n-type. So J and diffusion formula is Q times the diffusion constant dn times our value dn by dx. Okay, so we can substitute here, that is 1.6 into 10 to the power minus of 19 coulombs. What is the value of dn? 35 centimeter squares per second. 35 centimeter square per second times dn by dx, whose value is minus of 2 into 10 to the power 18 per centimeter to the power 4. So here your centimeter power 4 gets cancelled with centimeter square. So the value will be, if you simplify it, we will get the answer in minus. So here you, if you simplify it, here you will be getting minus 1120 amperes per centimeter square. Okay, so coulombs per second is amperes and here the value is centimeter square. So you have to be careful while calculating the units, and this is simple calculation. You can simplify and get the answer as minus of 1120 times ampere per centimeter square. So our answer is option D. Now let's move on to the 12th question. So in this question it is given, we got to assume electronic charge Q is equal to 1.6 into 10 to the power, this is minus of 19, not here, okay, to the power minus of 19 coulombs. Thermal voltage KT by Q is equal to 25 millivolts. So thermal voltage, that is VT, is given here. And electron mobility mu n, okay, the mobility is 1000 centimeter square per volt second. If the concentration gradient of the electrons, okay, concentration gradient of the electrons injected into the silicon sample is 1 into 10 to the power 21 per centimeter to the power 4. So here the electron concentration gradient, that is dn by dx, is given, which is equal to 1 into 10 to the power 21, that is 10 to the power 21 per centimeter to the power 4. What is the magnitude of diffusion current density in amperes per centimeter square? So here we got to find out what is Jn diffusion. So simple, we got to put the formula, that is Q times of dn times of dn by dx. So here dn is the diffusion, this capital Dn is the diffusion constant. Substitute the values of Q, 0.6 into 10 to the power minus of 19 coulombs. What is the value of dn given? So here dn is not given. Instead of dn, what is given? Mu n. So here we can substitute. So here, what is the relation between dn and mu n? Dn is equal to Vt times of, or Kt by Q times of what? Mu n. Okay. So we can substitute mu n and Kt by Q in place of dn. And what is the value of dn by dx? It is 10 to the power 21 per centimeter to the power 4. So here we can again substitute all the values to coulombs into Kt by Q is 25 millivolts. So here we need to convert millivolts to volts. So here 10 to the power minus of 3 volts into what is mu n? Mu n is given as 1000 centimeters square per volt second into 10 to the power 21 times centimeter to the power 4. Okay. So now we can simplify this. Volts gets cancelled. This 10 to the power 3 cancelled with 10 to the power minus of 3. And after simplification, we will be getting 4000 amperes. Coulomb per second is amperes. Amperes per, so here centimeter square cancelled with centimeter to the power 4, and we will be getting here centimeter square. So amperes per centimeter square. So our answer is 4000 amperes per centimeter square. So here 4000 amperes per centimeter square will be your answer. So in this question you can see at room temperature, that is 300 Kelvin, the whole mobility is given, that is 500 centimeter square per volt second. Thermal voltage is given, that is Kt by Q, which is equal to 26 millivolt. And the whole, we need to find out the whole diffusion constant, that is dP, which should be in centimeter square per second. So we know the relationship between the diffusion constant and the mobility. So here dP is equal to Kt by Q, that is the thermal voltage times the mu p. So here we can substitute the thermal voltage, which is 26 in terms of volt. It is 26 10 to the power minus of 3 volts because it is in millivolts, times mu p, which is equal to 500 centimeter square per volt second. So here volts gets cancelled and you will be getting, so here 0 gets cancelled with minus 3, and here we will be getting minus of 1, and if we simplify it we will get 13 centimeter square per second. So it is quite simple and straightforward question, that is 13 centimeter square per second. Okay, now let's move on to the next question. So here in this question what it is asked is, what is the ratio of mobility to diffusion coefficient in a semiconductor unit? Okay, what will be the ratio of the units obtained by the mobility and the diffusion constant, that is mu and capital D. So how mu and D are related? Mu and D are related with the help of the thermal voltage. So here D is nothing but thermal voltage Vt times of mu. So we need mu by D. So mu by D is equal to 1 by Vt. What is the unit of Vt? It is volts. So it is 1 by unit is V, that is volts, or we can write it as volt inverse. So our answer is option A, that is volt inverse. So that's it. It is all about the semiconductor part 2 gate questions. So in the next video we will be studying the semiconductor part 3, which will consist of the PN junction. So thanks for your time. Take care. Goodbye.